Okay, now we found that how this capacitor gets charged and discharged. So for example, so if you apply this kind of pulse, so the voltage across the or the source voltage is E. So during this cycle, so once you apply a voltage across this, so it's something like that. So we have resistor here, so we have capacitor here, and we have source here. So then this is E, this is R, this is capacitor. So once you apply the source, so this capacitor gets charged up to E. So it's something like that. So it's charged up to E and the value is remains as it is until then. So from here, what happens? So this capacitor is already charged up to E. At this point, your capacitor is already charged up to E. So then we remove the source. So then the circuit is something like that. So this is already charged up to E. So then it acts as a source having initial voltage of E, and whatever the stored energy is simply dissipated across the resistor as a heat. So this acts as a kind of a source initially, and whatever the stored energy is simply discharged through the resistor. Initially no stored energy across the capacitor, so we basically plug the external voltage source and power up, or the push a certain amount of charge to this capacitor. So after a certain time it got charged to E voltage, and then we remove the source from the circuit. So at that time that capacitor is charged up to E voltage, means it basically carrying certain amount of charge. So then once you remove the load source, so the whatever the stored energy inside this capacitor simply discharged through the resistive part. So then from here onwards it's basically discharged. So again, if you apply so once it's discharged to zero, so then you connect the same E source again to the circuit, so then it's again tends to charge. Okay, it tends to charge. Then again discharge. So then we found that during this block we have charging process. So during this block we have discharging process. Gain charging, discharge. So likewise, so this is the voltage we apply to the capacitor. So this is the voltage we apply to the capacitor. So it's vary between E and 0, E and 0. So it keep the certain time. So we basically apply E voltage for like t seconds. So then then we remove the E source from the circuit and keep it another t seconds. So then again we connect a source likewise. So then we can observe kind of a charging and discharging process of the capacitor. So once you apply a voltage, so it's basically charge the capacitor. Once you remove it, and whatever the stored energy at that point is simply released to the resistor. So this is the charging and discharging process of the capacitor. So what happens, like for example, Okay, so let's assume like this value. Let's assume this is t tau. No, so we'll assume that this is the value is basically tau. So this is tau naught. So similarly, we can have a same value. So this tau naught is the time taken to charge this capacitor up to E. So this tau naught is the time taken to charge the capacitor to E. Or so the time taken to discharge the capacitor to 0. So this tau naught represents the time taken to charge up to E or time taken to discharge up to 0 from this E value. Okay. So what happens if we apply a pulse with a pulse width of t less than tau naught? So what happens if you apply a pulse with the pulse width of t which is less than t naught? So then it's something like that. So if we draw it, something like that. So this is t. Let's assume this is like tau. So then this tau naught is the time that capacitor needs to charge its voltage from 0 to E. Now we apply a voltage only for a t value, t seconds, which is less than tau naught. So what happens to the capacitor? Ideally, if you apply a kind of fairly enough t value, so this capacitor is charging like that. So like that. But unfortunately, what happens is like before the voltage across the capacitor reaches to E, we remove the source. So then there won't be any effective voltage apply across the capacitor, and this charging process is suddenly stop at this particular point. So it means during this pulse, this capacitor is basically charged up to this level, not up to E. So if we maintain a pulse width of t which is equals to t naught, so it basically charge up to E. So if you switch the source beforehand, so when this t, capital T is less than t naught, so then this capacitor cannot charge up to E, but is basically charged to a level which is less than E. So then we know that during this period where you apply 0 voltage, so it basically discharged. Again, if this capacitor need to discharge to 0 level, it needs tau naught duration. But we know that during this block, so when this t comes to this, it again supply a voltage of E. So then this capacitor basically discharge whatever the stored energy across capacitor during this period. So it never discharged properly to zero. So it's basically stop at here. So then again we have charging. So then this. So then what happens if the pulse speed t is less than tau naught? So you have this kind of operation like that. So it never charged to E at it basically stopped beforehand. So it starts to a level where the voltage across the capacitor is less than E, and it's again discharged up to a level where it's not the so it basically discharge up to a certain voltage which is not equals to zero. If it is ideally or if it is completely discharging, so the actual voltage across the capacitor would be zero. But if it is not the case, so the voltage across the capacitor is slightly above zero, it's not exactly zero. So this is what happens if the situation is the other way. So then we have this kind of a scenario. So this is your t tau naught, this is your t, this is your tau naught, this is your t like that. So then this capacitor has enough time to make its voltage to its maximum. So this is the case where so we have enough switching time compared to the time that it needs to charge is to maximum or discharge is to minimum or zero. So if the t is less than t naught, so this capacitor never charge up to its maximum and never discharge up to its minimum. So it's never charged to E and it never discharged to zero. So it has a certain energy inside the capacitor. Okay. So if this is equals, so then you have kind of very perfect charging and discharging process. Like that. So this is like tau naught which is equals to t. This is again 2 tau naught which is again equals to 2t. So likewise. So this is the perfect situation. So this is t less than t naught, this is t greater than t naught. Okay. So from this we can have a kind of a conclusion. So what is that conclusion? If if tau naught is greater than this, what happens to the circuit? So it means so the capacitor needs a reasonably large time to pick up its voltage to its mechanism. So it means like capacitor needs a reasonably large time to pick up its voltage to its maximum. So if you draw it, it's something like that. So let's assume this is your download. So it's something like that. Okay. If you t is something like somewhere like here, and if your download is somewhere like here and t is somewhere like here, so we can claim that if this is the situation, we can simply claim that during this period, during this cycle, so the capacitor is not charging. So during this period, capacitor is not charging. Similarly, so if you consider the discharging process, if you consider the discharging process, if you consider the discharging process, so we can have the same argument like this. Okay. So in during discharging, so this is your download. So to make it like discharge. So if your switching period is like this, during this period the initial voltage dropped to this one, which is very negligible. So the initial voltage is dropped up to by very small amount during the switching period, capital T, because it takes download time, fairly large time, to make the voltage to zero. So then if this t is very small compared to t naught, we can similarly argue that it never discharges. Okay. So from this, so we can argue like that. If the switching period t is very small to this down, or the time taken to charge it to maximum or time taken to discharge it to minimum, we can simply argue that it means capacitor never charge or discharge. It means, so if you make the voltage, so let's do like this. So I'll do a small example. So this is the switching cycle. Okay. So it basically needs this much amount. So it basically needs this time to make it to charge to its maximum. So then if it wants to discharge its minimums, it needs this much of time. So what happens if we apply this kind of switching to capacitor? So it's charged its maximum because during this, let's assume this is t1, this is T2. So T1 is greater than tau naught. So then this capacitor charged its maximum and remains as it is. So during this cycle, so capacitor tends to discharge. So whatever the stored energy of the capacitor is simply released through the resistor. So it to discharge up to its minimum. So it takes this. So if we do this, so if so this is T2. So if this capacitor needs to discharge to minimum, it needs this much of time, but within this T2 period it cannot discharge up to that. It basically discharge it to here. So ideally we can assume that so this the voltage across the capacitor remains as it is. So if this T2 is very small compared to tau naught, so this capacitor doesn't have enough time to charge it to zero. So then we can argue that the whatever the stored energy inside the capacitor remains as it is. So next, once it got this positive cycle or this supply, so the capacitor voltage again keep as it is. So for this scenario, if the circuit doesn't allow to if the circuit doesn't allow to discharge the capacitor to its zero, so we can then it means like your tau naught is pretty much larger than the switching period T2. So then we can basically assume that this capacitor never discharged. Similar, so then we can basically argue that so if we have a quantity called tau naught, which is actually gives a kind of an indication about the charging and discharging time, if it is very large compared to the switching period, so then we can argue that this capacitor never charge or discharge. Okay, so this is the simple concept we use to explain the clampers. So if you are not giving a reasonably adequate time to charge the capacitor or discharge the capacitor, so then we can argue that that particular time is not enough to charge or discharge. So whatever the stored energy remains as it is, or it during that period there won't be any charging or discharging happens. So using that concept we can basically discuss the behavior of the clamping operation. So let's see the behavior of clamping operation next time, so with the help of this very basic concept.